In this video tutorial, we're going to discuss Adapt Post-Tensioning Optimizer, which will be new in Builder 2017. And for a basis of comparison, we're going to talk about how post-tension slabs, two-way slabs, are designed in the current version, which is version 2016 Build 4, and what to expect when using the optimizer in version 2017. And to do this, we're going to take a pretty simple example in Adapt Floor Pro. This is Builder 2017 that we're using, and we'll make sure that we set the units and the design scope to PTRC. We'll go ahead and launch the program, and we'll go ahead now and build our example model. So again, we're going to reference how this can be done in the current version of the program, version 2016.4, and how things will change in the next version, which is 2017. There's also a video related to the topic of tendon modeling in general and improvements that have been made for tendon modeling, replication, adding swerve points, adding and deleting spans more easily in the program, and we encourage you to visit that video also on our YouTube channel. So let's go ahead and get started. We're going to use the automatic floor wizard to generate this model. I'm just going to go ahead and close a few of these toolbars that are not necessary here to be open. And we'll go to Build, Floor Wizard, and we're going to create a model with two spans. And the span lengths will be 32 feet. Column size is going to be 20 inch square. The slab thickness we're going to use is 8 inches thick. There will just be one level, so we're just evaluating one floor for the design of the post-tensioning. We'll say next, and we're going to increase the live load slightly. We'll say it's 0.065 KSF, and the purpose, or excuse me, 0.06 KSF. The purpose of this is really just to force some stress issues, both tensile and potentially compressive, in the model, and we're going to focus on how we go about optimizing, or rather how we go about fixing some of those overstressed areas so that we can get a workable design. Optimization can be open, in meaning that you could have different solutions that achieve the same goal, which is to meet serviceability requirements. So our goal really is to meet those serviceability requirements and have a workable model that meets pre-compression, allowable tensile and compressive stress, and balanced loading. So we'll go to next. The level above and below are both 10 feet. The tendons in the floor wizard are input just on the basis of pre-compression. So for the distributed direction, we want to have 125 PSF. Same for the banded direction, we'll say 125. The effective force per strand that we're going to use will be 27 kips, shown here, and we're going to assume a CG in both directions, again just to simplify, of 1 inch for both directions. Now in reality you might have more of a CG here for banded direction depending on the detailing and the layout of the post-tensioning. For distributed tendons, we're going to assume that we have one strand represented by one tendon. So we could, for example, have bundles of 2 or 3 strands represented by one. Here we'll just say 1 so we can more cleanly review the input when we build this model. So we'll go ahead and say next, or end, excuse me. And this is the model we're left with. We have the banded tendons in the Y direction and the distributed tendons in the X direction. Now one thing you'll note is there's a few more descriptor points located on the tendons, and what these are is we have, for example, the red point here is the control point. It's the high point. I can move that point. I have the low point, which is shown by the blue symbol, another control point which is a high point over the second or interior support, low point, and then the other high point on the opposite side. At the ends of the tendons I have an automated swerve point, which is a property of the tendon. So if you open the tendon dialog menu, you'll see that we use auto swerve points, and this just allows us to move this endpoint if needed, and if we add swerve points to other locations of the tab, that gives us the ability then to maintain the angle at which the tendon is locked to the slab. We can see at the end of the tendon we have this blue X, which represents an anchor point. So currently this tendon is set to 90-degree anchorage to the slab. If I was to move the slab, and I'll go ahead and do that, let me reset the view and I'll turn the tendons back on. If I move this slab, for example, you're going to find that these tendons are still anchored then at 90 degrees relative to the slab edge. So that gives us an option to set that anchorage angle and also to just release it so that it's free and it doesn't have a link between its orientation relative to the slab edge. So this will be the model we're going to use as a basis again of comparison. So let's go ahead and save the model. And under the load combinations, we're going to be evaluating really the service total combo. These are just the default combinations that are assigned based on the code that we're using here. It's ACI 2011. We're going to be focusing mainly on meeting the requirements for serviceability at total service condition. So we'll be using this combination when we use the optimizer and then when we evaluate the stress for the slab. So let's go ahead and run the analysis. We'll go to FEM. We're going to mesh the structure. Once the structure is meshed, we're going to analyze again from FEM. We'll analyze the structure so that we can obtain results for the model. So I'll analyze the set of combinations here. And before we generate our design strips and our design sections under criteria, you're going to see that for the allowable stresses, we're setting these to 6 times square root of f prime c for total and sustained condition. The compressive limits are shown here for sustained and total, and then for initial transfer we have these conditions. So those are the allowable tensile and compressive stresses that the program is going to be using and referencing once we get into Optimizer. We'll just say OK, and now what I'll do is let me clean the view again. I'll just go to my default display, which doesn't have any of the tendons shown. We'll go to strips. I'm going to generate my design strips and design sections. So now we're left with an analyzed slab. We've generated the strips and the design cuts for those strips. If I view the design cuts using the Display Design Sections tab, I'll just look at the X direction. We have 3 strips in the X and then also 3 strips in the Y. Now it's important to note that when we first set up our tendons, we set those up only to meet precompression. So let's go ahead now and design the strips. I'll go to FEM, design the design sections. We'll use the design option, not the investigate option in this case. We'll say yes to save that, and now we have a result. So I'll look at the X direction. It's a little easier to look. The results are similar in both directions given the symmetry for the model, and we're going to focus mainly on let's take this middle strip. It has the widest tributary. However, it also has more post-tensioning than the other strips in order to meet the P over A over a greater area. So for service total, what we'll do here is let me use the result display settings under the design sections tab to view some of the results for this particular model. So I'll shorten that tab or that window. And for example, for precompression, if I use P over A number of tendons, this is just a geometric check of the precompression in the slab. It's just the number of tendons, the total force inside of a given section divided by the sectional area. So it has really nothing to do with the axial force as a result of the finite element result. It's similar to the P/A check in ADAPT PTRC, which assumes that the slab is just allowed to freely shorten, and any necessary detailing related to restraint mitigation would be taken care of. So this result is a simplified P/A result, and you can see that my setting under result display settings, the P/A is set to 125 as my allowable. We also have maximum precompression here, and we'll set that to 300. And if I turn on the numerical display for the strips, this is about 132 psi for precompression. On the opposite end, we're right up near 140, and on the lower end, again 140. Now the strips at the edge of the slab, if I turn on my tendons, you can see there's a bit of a drop off there, and we get a drop off at these locations due to the presence and the discretization really of the tendons, the elements within that zone on the boundary of the slab. So we're going to just ignore that, and we're going to focus more on the overstressed regions for a comparison of actual stress, flexural, combined flexural and direct stress or precompression against the allowable stress of 6 square root of f prime c. So if I go back to the analysis checkbox in the result display settings, I'm going to look at the bottom stress, and you'll note that for almost every span in this case, both x and also y, the bottom stress midspan is overstressed. The allowable is based on a setting for material of 4,000 psi, and the allowable being 379, and you can see the allowable is actually shown here, 379.5. We have an actual stress of 514, 529, 536, and so on, and it's pretty close on the opposite side, just again due to the symmetry in the model. And again, looking at top stress, we have an overstress, which is at this is the controlling overstress. This is quite a bit higher. If we were to take a ratio of actual stress over allowable, this is much higher than what we had for the bottom stress. So this might control our design at this point. So in the current version of the program, the question then becomes, well, how do we go about solving this problem? And what we would have to do is we'd have to make modifications manually to the slab and then rerun the slab to get us to a closer workable design. So for example, and a lot of this is based on experience that a user might have in solving situations like this. Some of it is trial and error. Some of it might be using more of the partial optimization within the program. In this case, if I turn on my tendons, what would be required is for the user to make modifications to the total tendon number of strands, or the total tendon force, the effective force per strand, or potentially a combination of both. So if we were to try and solve this overstress in the current version, we would likely go in and we would limit, or we would keep the effective force at 27, and we would start adjusting the number of strands per tendon. And that might require some manual calculation on getting us in a workable range for stress, other than simply just guessing in this case. So one thing we could do to begin is we could assign a number of strands for the tendons tributary to this strip such that we would get the highest maximum P/A in the slab. Currently we have a P/A of around 140, so the next thing we may do is increase the number of strands to max out P/A of 300 to see if that brings us into a workable range. If it doesn't, then that means we're likely going to have to increase the slab thickness in this example. So that becomes an iterative process in the current version, or in the current version 2016.4. In version 2017, we have another option. We have the optimizer. And let's go ahead and turn off our tendons for just a moment. we're going to focus in on this span here, which has a overstress at the bottom. It also has an overstress at the top that we just saw in tensile stress. So we have a top fiber exceeding tension, bottom fiber at midspan exceeding tension. And we want to use a tool that allows us to do this a little more quickly and more efficiently so that we can go through this cyclical nature of the design more efficiently. And one other thing to take note of is the balance loading. So if we turn on balance loading, we can see here we're at 41%. So we clearly have room to work with in terms of load balancing for this particular span and also the adjacent span. These are roughly around 40% total dead load. This is in terms of the total dead load. So let's go ahead and turn off our result display settings for a moment, and I'm going to turn back on my tendons. Actually, we'll clean the screen and then turn the tendons back on. And we want to optimize the tendons beginning here, and we're going to basically optimize all of these tendons that we're selecting here, from here down to here. That's the amount of tendons tributary to that frame line or that design cut that we're looking at for midspan and for support. So on the tendon toolbar, and we'll go ahead and move that toolbar down into the main graphical space, there's a new button here that says Optimizer. We'll go ahead and select Optimizer, and you'll notice once we select that the control points, or excuse me, the low points become yellow. So these are just essentially handles that we can select tendons to be included in the optimization that we're going to run for this particular model. And what we'll do is we'll set and select the tendons that we want to use for this optimization. So I can window select, or I can individually pick the points and select control. We'll go ahead and select these tendons. And the program will run through an analysis based on the previous solution, or the saved solution rather, as to the existing or the current status of this particular span. So we're really optimizing one span out of this strip. And you can see if I zoom in, the program shows you the window of the tributary. Okay, so because I selected these tendons here, the tributary that the program is evaluating is signified by this blue box. And note that the program also creates 3 virtual design cuts. They're not part of the support lines that we generated earlier. These are just on-the-fly creation of design cuts for the purpose of the optimization. So we can see that in the view we have a section cut here, this magenta color at the left support, the mid span, and also the right support. This is section cut A. We have section cut B, which is in the middle, and then section cut C at the right side. And the program creates those automatically when we optimize. If we look at the tendons in the optimization, the program numerically labels a tendon. So this is tendon 1, 2, 3, all the way up to tendon 15. And there's a little bit of data given for each of the tendons. The strand is 1, the effective force is 27, the CGS is 1, and it gives us information for each of the tendons as they currently are in the model. Now the optimizer has several different tabs. We'll come back to the optimizer tab. We're first going to go to the calculations tab. This is just simply output for the calculations of the optimizer. So if you're interested in seeing the calculations, how things are being calculated, whether it be the tributary areas, selected values, this is total force, force over length, total strands, inputs like min and max range for CG, precompression, stress level, etc. This is just a mirror of the calculations going on behind the scenes that are available to the user. The settings tab allows the user to set criteria necessary for the optimization of the selected tributary. The first block is the tributary width settings. So in this case, the The tributary that I selected is a 32-foot tributary. The program allows us then to set the end section cut as a percentage of the span. So the section cuts at the end, here and here are some percentage of this span length over the tributary. So from this column, let's say, over to this column. And we can modify either of those. We can modify the tributary width that we want to optimize by just user override here, or the end section cut as a percentage of the span, and then we update. We also have the ability to choose how we want to display load balancing, and so we can display it in terms of self-weight only or self-weight and dead load. One thing to differentiate between the current version is the current version by default, version 2016, allows you to change this, but it always uses self-weight and dead load as its default. You have to actually assign superimposed dead load as a user-defined load case rather than the predefined dead load case if you want to limit the current version to checking this as self-weight only. So this gives the user just more flexibility, just easier input versus the current version. We also have how do we want to report the stress. So we have the option to give you the format for stress value. Is it a ratio? For example, if stress is 6.2 divided by 6, which is the allowable, the ratio would be greater than 1. So this is just the stress is in terms of a ratio. We can also show stress in terms of the actual value. So this reports in MPa or in PSI, and also in terms of a factor shown in the middle, and this is currently inactive at the moment. So we're gonna focus on ratio versus actual or factored. For the desired ranges, these are the ranges that we wish to optimize when it comes to pre-compression and load balancing. We'll reference Adapt PT as a comparison, and in that program the user inputs ranges min and max of both of these values for that program's algorithm in determining the number of tendons or the total force in the CG. This is similar in nature to that program in terms of optimization. So for this example, we're going to leave the pre-compression set to 125 minimum, 300 max. The load balancing is 50 and 100. Now the min and max here, if we modify these, those are also going to be modified in the result display settings or the red eyeglasses. If you recall earlier, we looked at the min and max pre-compression. Those would be reflective of what's going on here also. The load combination that we're going to be satisfying here is service total. So those factors associated to this combination and the resulting moments and axial force, etc., that are reflective of this combination will be used for the purposes of the optimization. We have the ability then to select any combination that's tagged as service that we can optimize to. This would yield the most conservative result because there's more load associated with total than there is sustained for this example. The criteria is two-way slab, so this means that whatever is selected here, the program pulls the allowable stresses from, set in the criteria, and so on. And this is important to tag this as what is really being designed for in the model. The stress allowables then come from this criteria setting. So this is read-only. You can see this is US units, two-way slab, total service condition. The top stress is 379, that's 4,000, or square root of 4,000 times 6. The bottom is 379, and then the compressive stress for total service is 0.6 times 4,000 psi, which is the 2400. We can also choose which parameters we want to optimize for. So if we're only concerned, for example, about pre-compression, we could turn off load balance and stress. The program would target the optimization inputs for pre-compression only, or we could do load balancing, stress, a combination of all three, or select all of them. Selecting all of them, again, as compared to Adapt PTRC, is similar in nature. In PTRC, the program is always optimizing to all three, so this would be reflective of that type of a algorithm in terms of the post-tension optimization. There's also a setting here using whole number of strands per tendon. So if we want the program, if we want it to refine the number of strands, we can leave this turned off, and then we have the ability for the strands to be in decimal format. Otherwise, if we select this, the program will always round up, and we would potentially have more force in a given tributary than what might be required. So it's a little more conservative to use whole number roundup in this case. If we look at the Details tab, this is a reflection of the current status and the optimization and estimated status given the values that the optimizer is suggesting. So for example, we have again a US two-way slab system. The current force in this slab, if we were to sum up the force of all 15 tendons, is 405 kips. If we divide that force by the tributary of 32 kips, we get 12.66 kips per foot. The total number of strands is 15, and the CGS here is 1. This is 1 for each of these strands. The load balancing in terms of self-weight only is 49.47, so it's slightly under the 50% value that we had in settings. Now if we change this to self-weight and dead load, and I go back to Details, you can see this number gets modified. Now we're even less because we have more total dead load that we're accounting for in the calculation. It's still less than 50%, so it's flagged as red. We'll go back to settings, and I'll change that back to just self-weight. The current stress ratio, negative is compression, so if we have a negative value, then the negative will be reflective of, again, a compressive state. If that compression ratio goes below the compression threshold, then this would actually be flagged red. It's rare that that would happen, but it could happen in a design where you have an overstress in compression. At each of the section cuts A, B, and C, we show top stress, the pre-compression. This is the current pre-compression for this particular section cut. And note that we report both FEM and number of strands. Previous, when we looked at the pre-compression along the design strips, we looked at the number of strands. So there's two outputs where P over A for FEM is really taking the axial force divided by the area versus the total strands times our force divided by the area. And the only difference there is that the FEM result accounts for any axial deformation. It accounts for restraint due to supports, due to walls, anything that would cause restraint or lack of shortening in the slab in plane, that would be accounted for in the FEM result. So there's a slight difference here. That's to be expected given the reasons just outlined. The bottom stress, again, at A, B, and C, we just show the bottom stress values. So at the support, we would expect top stress to be in tension. You can see this is less than 1, so that means our stress is less than the 379. At midspan, the top stress is in compression. And at the middle support, this is the support we were having issues with, and I'll mark that support right here. We were having an overstress there of roughly by a factor of 2 or slightly over, and that's reflective right here at 2.361. So that tells us that we have an issue in top stress. For bottom stress at section A, we have compression. Again, that makes sense at a support, compression at the opposite end, but we also have an overstress in tension at the bottom of midspan, which is here. Again, these two issues need to be solved, and we talked earlier about how we would have to solve them in the current version, again 2016.4, and what can be done in this upcoming 2017 version of the software. Okay, so the optimizer status is reflective of what the program is suggesting for an optimized value. So we're now going to go to the optimizer here, and then we'll come back into this to look at the details of the optimizer. So the first thing we see in the optimizer is this graphical view of what's going on with this particular strip. We can see that the current force, and I'll use my pointer here to show what I'm referring to, the current force is set to 405 kips. That was shown earlier in details. The current force is 405, the total number of strands is 15, CGS1, and so on. The range of precompression between 125 and 300, which were our inputs, the force associated with a precompression of 125 is 384. The force associated with a precompression of 300 is 922. So this shows you the lower and upper bound for precompression and load balancing. A force necessary to meet 50% balancing relative to self-weight is 409. So clearly that's why we're off by a percent or two. Our current force is 405 and the necessary force to just meet 50% is 409. And the force necessary to meet 100% load balancing reflective of or relative to self-weight is 819, and we're over that. We're way down here at the lower end, so we're not even meeting our minimum load balancing target. In addition to the current value that's shown, the program also shows the estimated force necessary to optimize the design, to meet the targets for this design. So the force that's estimated of 893, and that value is also shown here. We also report it in form of strands. So rather than having 15 strands in this zone, we would need 33.08 to meet that force. We have a CGS of 1. We're not changing the CGS here. The precompression jumps from 131 up to 290, assuming this force. So we're still okay. The upper bound precompression is 922, but we can see, looking at this line, if we were to increase the force to 893, we would exceed load balancing, and we would exceed it by about 10%. That's shown right there. So now we have a decision to make. Do we want to apply this modification to the model automatically, or we can also edit this manually? So if we were to, for example, select edit to manually modify, and then we might want to increase this to 920 kips, the user could then estimate, select the estimate button, and the results would then be reflective of the new entered value by the user, which is 920. So we overwrote the optimization. The program would still report some calculation status. We're still exceeding load balancing, which is here. We've now increased that overage in load balancing. We have also modified some of the forces and the stresses shown here. So at the very bottom you can see the minimum force necessary to meet stress at each of the sections is shown here. So we only need 893 kips at section C, or 546 at section B, and we have input 920. So we'll go back, and I'm going to turn off edit. That goes back to the optimized value. You'll see that also under the estimated value, the program again reports total strands, CGS, precompression, and so on. So if we want to accept a change based on the optimization or based on our edit, we have the ability to apply this to the model. So if I go ahead and select the option to apply the change to the model, we realize that we're a little bit above balanced loading, but that might be something we have to live with in this case due to other constraints in the design. So noting that load balancing may not be an actual code requirement, we're going to assume we can live with a slight overage in load balancing for this particular span, and we'll select apply to model. Now the program gives us additional options on how to apply this to the existing model. And we have different ways to apply this. We can apply this as a distribution to the 15 selected tendons that are shown. Here we have 15 tendons. The total force change, the delta between the existing force and the new force, is 488.2 kips, so that's a change of 32.55 kips per tendon that's modeled. The strands, we need 18.08 new strands. That's 1.21 in addition to the one already in place. So each of these in essence would grow from one strand to 2.21 strands. And then we could also set the CGS value to each of those tendons that are now going to be added to the slab in this particular span. We also have the ability then to rerun the model. So if we wanted to apply the change and then rerun the finite element solution for this model, we could select and tag this, select apply, and that would force a rerun of the analysis. If we apply and we do not reanalyze, we cannot come back and edit this span until the analysis is performed again, because we need to update the solution to have a basis to check against once we re-enter the optimizer for the same span that has previously been optimized. So that's something to be aware of. In addition to a distribution of the change, the force change, we can also add a single tendon. So for any of these tendons that are currently modeled as cantilever, span, span, cantilever, so there's two full spans and two cantilevers, they're just one long tendon line. If we wanted to just simply lump this 488 kip into one tendon, we would select the tendon to modify, and tendon 1 is at the bottom. I'll go ahead and mark that. There's tendon 1 here, moving up to tendon 15, which is up at the top here. And we have the ability then to modify any of the tendons within the selected range. So if we modify tendon 1, for example, we would estimate or assume an effective force of 27 kips. Again, the program shows us how many strands are going to be added to this particular tendon. And if we select apply now, then at tendon 1 it's going to grow from one strand up to 19.08 strands, because we're adding additional strands to the model. The last apply options input would be add tendons. This is just another selection. So this gives us more ability to control discretely where the tendons are being added for this force that's required, the delta necessary to meet those serviceability stresses, 6 squared of f prime c. So in this case we have a few inputs that the user should be aware of. First, we want to select the tendon to duplicate. So this duplicates the shape of the tendon and the effective force of the tendon. We have 15 tendons in our range, and we want to determine which tendon, for example, we want to match. Now all of these have the same shape and profile in the cantilever and in the span and the same effective force. So here we're just going to use one as our duplication tendon. So it's really a template tendon we'll use for applying add tendons. The program again shows us the total force differential needed to be added to the tributary. It's 488.2 kips. The number of strands is 18.08 kips, and again the CGS is 1 inch. Now for add tendons, the program has two inputs. One can be create the number of tendons. So if, for example, we wanted to begin adding tendons between tendons 1 and 2, which are already in place, and we wanted to add a tendon in each gap, we would select here the number of tendons. So we want to select 14 tendons. This data will change based on the number of tendons we wish to add to the slab, and this tells the program where to start the tendons. If this was, for example, set at tendon number 13, and we wanted to add 14 tendons, the program would loop back. It would add 1, 2, and then loop back down to the bottom, 3, 4, and so on. So this allows us to select add tendons. Now the add tendons can be full tendons. They can be throughout the entire slab, and they basically are replicated based on the duplicate tendon, tendon number 1. We can also do partial tendons from section A to the edge of the slab. So this is basically an add tendon where we would select, we would basically anchor a tendon here, and this tendon would pull out of the slab on the far right side. the second option here, add partial tendons from section C to edge of slab, we'll have a reverse and opposite add tendon. So this would actually be something like this. And then we have add partial tendons alternating from A to C. So that would be a alternating add tendon. So if we had 14 tendons, one would be this direction, the next one would be this direction, and so on. The program would alternate the add tendons within the range that is selected. In this case, the most efficient way to probably do this would be to add the tendons at section C, and we input a percentage of the span where the tail terminates, shown here, and then we would go ahead and apply that, and that would add those tendons to the model. Now for this example, we're going to go back to distribute, and we're going to distribute the change across all of the strands. And this change is going to be reflective not only of this span, but the entire 2 spans and 2 cantilevers. So we'll go ahead and say apply. And note that once we apply this optimizer, the inputs here are locked out. The program shows you that the current status is now the previously selected optimized status. However, we have to rerun the analysis to essentially reset this current value in order to optimize again. If we wanted to optimize this span again, let's assume we added more load or changed something geometrically where we wanted to re-optimize. So if I go ahead now and close this and I open Optimizer again, you'll see that these tendons that we just optimized are currently inactive for optimization. They do not have the yellow active handle on them, so we can no longer optimize these strands until we reanalyze. We'll now go back to FEM, and we're going to reanalyze the structure and then redesign the sections for the design strips so that we can evaluate the current level of stress in the slab, having considered the optimization that we used for the span in question, this middle support line span. So we've analyzed, and now we'll go back to FEM and design the design strips. And we'll go ahead and just turn off the view of the tendons. I'll view the X direction support lines, and here we can see that even though we optimized this span for the middle design strip in the X direction, we still have an overstress. So the allowable is still 379 psi, and we've reduced the stress from over 1100 psi down to 564. Now the difference being that when we use the optimizer, the program isolated one span, and it looked at that span as a unique span that it was optimizing, similar to what would happen in a 2D program like Adapt PTRC, where we recycle or we use a recycler to optimize post-tensioning for an isolated frame line within a larger three-dimensional model. And that's the same thing that's happening with the optimizer. And in reality, when we go back and rerun this as a finite element model, we have part of that precompressive stress or force from the post-tensioning, which distributes into the full region or full width of the slab versus being isolated within one discrete location, or one span in this case, and only being considered for that one span. So the process becomes iterative, and it becomes agile. We consider this agile design in Adapt Builder. We have a companion video that goes through more details about the process of agile design using the new optimizer, and we recommend all users to view that video as well. It can be found on our YouTube channel at www.youtube.com/adaptsupport. If you have any questions, please contact our support group at support@adaptsoft.com.